All right, here are solutions to the worksheet that you guys will be doing for Thanksgiving class, I guess for the Wednesday before Thanksgiving in lieu of actually coming to class. There's two problems here. In the first one, you were given this polynomial, this third degree polynomial, and you're asked to list all possible rational roots. So what rational numbers could possibly be a root of this polynomial? Well, possible rational roots always take on the same form. They are factors of the constant term divided by a factor of the leading coefficient. So in this case, it's a factor of 6. So the factors here are 1, 2, 3, and 6, divided by a factor of 2. So 1 or 2. So 1 divided by 1 would give me 1. 2 divided by 1 would give me 2. 3 divided by 1 would give me 3. 6 divided by 1 would give me 6. And then I can take each of these four numbers and divide them by 2. So 1 divided by 2 gives me 1/2. 2 divided by 2 gives me 1. I already have that. I don't need to write it again. 3 divided by 2 gives me 3/2. And 6 divided by 2 gives me 3. I don't need to write that again because I already have it. So here are, I put in the plus or minuses to account for the signs, and I get 12 possibilities. These are the possible rational roots of this polynomial. They're not all roots. It's just the only possibilities for rational numbers. Part B says, all right, go test those ones so you find one that works. But really, I don't want you to just start testing them blindly because I don't want you spending forever doing this. So instead, I tell you, yeah, 2 should work. So show me how you can test 2. Well, what I mean by test is you can take 2 and put it into your polynomial. And if 0 comes out, that means that 2 is a root of your polynomial. So if I go changing all my x's into 2's, I get 2 times 2 cubed minus 9 times 2 squared plus 7 times 2 plus 6. And let's see, 2 cubed is 8, times 2 gives me 16. 2 squared is 4 times 9 gives me negative 36. 7 and 2 is 14. 7 times 2, that is. And then 6 more. And 6 and 14 gives me 20, and 16 more is 36. I subtract 36, sure enough. This equals 0. What I'm saying is if you put 2 into this polynomial, 0 comes out. Therefore, 2 is a rational root of this polynomial, or a root of this polynomial that happens to be a rational number in this case. Part C says, all right, there's this thing called the factor theorem. This says anytime that r is a root, x minus r is a factor. So I can apply that to learn that x minus 2 is a factor precisely because 2 was a root of this polynomial. And the minute that I know that x minus 2 is a factor, that means I can do polynomial long division. X minus 2 divided by my polynomial, which was 2x cubed minus 9x squared plus 7x plus 6. And when I do this polynomial long division, I better get a remainder of 0 because x minus 2 should be a factor of this polynomial, so it should divide in evenly. So let's go through and do the polynomial long division. To get rid of this 2x cubed, I'd want to put a 2x squared up here because 2x squared times x minus 2 gives me 2x cubed minus 4x squared. And then if I subtract, these guys go away. Negative 9x squared minus negative 4x squared gives me negative 5x squared. Be careful there. Not negative 13, for example, x squared. And you bring down that 7x and you repeat. To get rid of this negative 5x squared, I need a negative 5x up here. Negative 5x times x minus 2 gives me negative 5x squared plus 10x. And I subtract. These cancel out. 7 minus 10 is negative 3 as the coefficient on my x term. And then I bring down the 6. To get rid of the negative 3x, I write a negative 3 up here. Negative 3 times x minus 2 is negative 3x plus 6. I subtract, I get 0. Which I was expecting to get 0. That's a nice built-in check on these problems. Remainder of 0 tells me that x minus 2 divides evenly into this polynomial, so I can begin factoring my polynomial. I can write it as f of x equals x minus 2 times 2x squared minus 5x minus 3. It's not completely factored, but I've begun factoring this thing. Part E says, all right, finish then. You got this far, finish it up. Factor 2x squared minus 5x minus 3. Well, there's a couple ways you can do that. It's kind of this guess and check method. Or if you want to go through the process, the longer process that we learned as an option in class, you can find two numbers that multiply to negative 6, the product of A and C, and add to negative 5. So what, positive 1 and negative 6 would work? So I replace the negative 5x with positive 1x minus 6x, and I can factor by grouping. For my first group, I have a common factor of x, greatest common factor of x, and that leaves me with 2x plus 1. If I want to be left with 2x plus 1 over here, I better factor out a negative 3 for my second group. Now what I have are two terms that both have a 2x plus 1 in them. So I can pull out that 2x plus 1, and all that I will have left would be x minus 3. What I'm saying is that the factored form of my polynomial is this x minus 2 times this 2x plus 1 times this x minus 3. So here, factor the quotient from part T, done to obtain the factored form of f. There you go. Determine the x-intercepts of f. All right, now that you've done all that work, finding the x-intercepts is pretty easy. Find the x-intercepts of f. You just solve for the x values that makes this thing equal to 0. Well, when it's in the factored form, you're just saying x minus 2 times 2x plus 1 times x minus 3 equals 0. That happens if any of those factors equal 0. So if x minus 2 equals 0, or 2x plus 1 equals 0, or x minus 3 equals 0. So if I solve these three equations, if I add 2 to both sides of the equation here, or subtract 1 and then divide by 2 here, or add 3 here, I get the x-intercepts. So I got 3 x-intercepts of this polynomial, all this work to figure out those 3 x-intercepts. Make sure that you can take this further. Make sure that once you have the x-intercepts, you know how to determine their multiplicities. They're each 1 in this case. And then know how to graph that polynomial. So express the end behavior of the polynomial. Find the y-intercept. Draw through the x-intercept with the proper behavior based on the multiplicities. Make sure you can do all that stuff for this problem. Next one. All right, in this one, I am told I have this new polynomial g of x, 4th degree polynomial this time. And I'm told negative 1 plus 2i is a root. Just told that. How do you know that? I don't know. It's just given. Somehow you know that. Wow, it's close. Shouldn't be watching football at the same time. So if negative 1 plus 2i is a root, well, complex roots always come in conjugate pairs. So if negative 1 plus 2i is a root, that guarantees that its complex conjugate, aka negative 1 minus 2i, must also be a root. So this first one is just recognizing that fact. Complex roots always come in conjugate pairs. Now it's saying, using these two roots, negative 1 plus 2i and negative 1 minus 2i, come up with two factors of this polynomial. That's my factor theorem again. If r is a root, x minus r is a factor. So if negative 1 plus 2i is a root, then x minus that thing, negative 1 plus 2i, is a factor. If negative 1 minus 2i is a root, then x minus that thing, negative 1 minus 2i, is a factor. So I get these two factors of g. Normally when you have a factor, you're thinking polynomial long division, but not when your factor involves complex numbers. So in part C, I tell you to multiply these two guys together, because if this divides my polynomial and this divides my polynomial, then their product will also divide my polynomial. But a nice thing about the product that occurs from the factors that correspond with conjugate roots is that that polynomial will only have real coefficients. What I'm saying is if you FOIL this thing out, all the i's will go away. Don't trust me? Just watch. X times x gives me x squared. X times negative 1 minus 2i gives me negative x times negative 1 minus 2i maybe. X times negative 1 plus 2i. X times the negative of negative 1 plus 2i gives me, well, let's see, I'm taking a positive times a negative, so I'll put a negative here, and then my x, and then what was in the parentheses, the negative 1 plus 2i. And then for the L in FOIL, I have this minus times this minus, so that makes a plus. Plus what? Well, the product of negative 1 plus 2i and negative 1 minus 2i. So this doesn't look any better, but if you simplify a little bit, I got the x squared. I can take this negative x and distribute it through. So negative x times negative 1 gives me positive x. Negative x times negative 2i gives me maybe plus 2xi. Negative x times negative 1 gives me another plus x. Negative x times positive 2i gives me a negative 2xi. And then if I FOIL out here, negative 1 times negative 1 is positive 1. Negative 1 times negative 2i and negative 1 times positive 2i will cancel each other out. And then minus times that positive gives me a negative 4i squared. So I got an x squared. I got an x and another x to give me 2x. I got a 2xi and a negative 2xi. Those cancel out. And a 1 plus 4, because I squared is negative 1, gives me a 5. And this is looking a lot nicer. This only has real coefficients. So what I just came up with is a second degree polynomial that evenly divides this guy. This divides into this. So what that means is I can do polynomial long division. I can take x squared plus 2x plus 5 and divide it into my original polynomial, which is what, x to the 4th minus 2x cubed plus 2x squared minus 10x plus 25. And I can do polynomial long division. And when I do polynomial long division, I better end up with no remainder, because this is supposed to divide evenly into this, because it came from two factors that came from two roots of this polynomial. So to get rid of this x to the 4th, I put an x squared up here. X squared times this polynomial gives me x to the 4th plus 2x cubed plus 5x squared. And I subtract. X to the 4th minus x to the 4th goes away. Negative 2x cubed minus 2 more x cubed give me negative 4x cubed. Where was I here? 2x squared minus 5x squared gives me negative 3x squared. And then I can bring down the negative 10x, and I repeat. To get rid of this negative 4x cubed, I need to put a negative 4x up here. Negative 4x times x squared gives me the needed negative 4x cubed. Negative 4x times 2x gives me negative 8x squared. And negative 4x times 5 gives me minus 20x. Subtract again. 4x, negative 4x cubed minus negative 4x cubed cancels out. Negative 3x squared minus negative 8x squared is positive 5x squared. Negative 10x minus negative 20x is positive 10x. And then bring down the 25. And if I go through this one more time, if I throw a 5 up top to get rid of this 5x squared, what I'll end up with is exactly 5x squared plus 10x plus 25. So when I subtract, my remainder is 0, which is a good thing. That tells me that my polynomial can be written as x squared plus 2x plus 5, which I already had, times this quotient, x squared minus 4x plus 5. I already got two roots out of this polynomial, or more accurately, I got this polynomial out of two roots. But now what I got to do is get roots out of this polynomial here, out of this factor. How am I going to do that? Well, I'll set it equal to 0. I'll take x squared minus 4x plus 5, set it equal to 0, and solve. You got options. You can use the quadratic formula, or what I'm going to do is complete the square. So to complete the square, I want to get the x squared and the x term all by itself. So subtract 5 from both sides. And then I want to add some number to both sides of the equation so that I'll have a perfect square. That number's positive 4. And what that'll leave me with is a perfect square on the left-hand side of the equation. In this case, x minus 2 squared. And so I can solve this equation for x by taking the square root of both sides of the equation. So I got x plus 2 equals plus or minus the square root of negative 1. Sorry, x minus 2 equals plus or minus the square root of negative 1 is just I. So the two complex roots that I get are x equals 2 plus or minus I. Note conjugate pairs. That always happens when I have conjugate roots, as I talked about in part A of this problem. So I end up with 4 complex roots, these two and the two that we had from up here, this guy and this guy. And that's all I wanted you to do on this one. All I wanted you to do. That's kind of a lot. But I'm going to end this video here. I hope you guys have a good Thanksgiving, and I'll see you when you get back.